Okay, I'd like to welcome everyone to Denby Dale Amateur Radio Club this evening. It's great to see you, and a big welcome to visitors. It's fantastic tonight. We've got a speaker, Ian Morison, who's Professor Ian Morison, in fact, from the Jodrell Bank Observatory, who also very kindly changed his name when he entered the room here tonight to put his call sign in, because he's a radio amateur, G0DMU. So a big welcome to Ian, our speaker tonight, who's going to give us a talk on the story of Jodrell Bank. Ian is an astronomer and a radio astronomer. Of course, he's not the first one who's a radio amateur to get into radio astronomy, and anyone who's got an interest in astronomy will know that one of the first people in the world who developed a radio telescope and started to map objects in the sky using that radio telescope was a guy called Grote Reber, W9GFZ, in the US, who built in his back garden a 9-meter radio telescope in 1937, and is one of the early founders of using the tracking of radio waves to look for objects in the universe and in the sky. So Ian, you've got a good antecedent with you there. If you wouldn't mind, I'm just going to hit Ian's button. Ian, I'm going to hand the microphone over to you, and you can obviously introduce yourself and start off. So the normal process we're following with Ian tonight is Ian's going to give us his presentation, and then we're going to throw the discussion open to any questions to Ian and any discussion on what they've heard. So Ian, over to you.
Very good. Now I want to share screen, and there's a thing about sharing sound, which I've clicked on, and this is what I think. Can anybody see that? Just thumbs up. If you can.
We can. It's great.
Oh, very good. And you can hear me as well, I hope.
We can indeed.
Good. So anyway, the story of Jodrell Bank. I sort of became the sort of in-house historian, really, particularly around the time of our 50th anniversary. I had to give lots of talks about it. And I think I developed this talk about then. That was quite some time ago, but things change, and I keep on updating it every time I give it. So I hope you enjoy it. So let's begin. The story actually begins at a radar station, the Chain Home radar station at Staxonwold, which is above, or was above, Scarborough. Now, Bernard Lovell had been studying cosmic rays at the University of Manchester, and he was called up to help develop radar. In fact, he got the OBE because he led the team that developed the H2S radar. That's the one where a line sort of goes round in a screen and leaves little blips behind it. So he was very, very good during the war. He did a lot of good work. Anyway, he was at this place the morning that war was declared. And he was a rookie. He didn't really know much about radar and the things that were going on. And he got very perturbed when he saw quite a number of echoes on the radar screens. He said, well, why aren't you sending up any fighters? They said, aha, those are echoes, but they are not aircraft. We do not know what causes them. They come and go a bit. We call them sporadics. Now, he knew there was a method whereby a high energy cosmic ray could give rise to a shower of electrons that would reflect radio waves. So he thought that radar might be a way of studying cosmic rays. In fact, he wrote a paper during the war about this, and happily for us, he left out an enormous damping factor of getting on for 1 million, which meant that it was totally impossible to detect cosmic ray air showers by radar. But had he not made that mistake, Jodrell Bank would never have happened, and I wouldn't have had a job for many years. Anyway, so the sporadic echoes were really the origin of the Jodrell Bank Observatory. When the war ended, he was able to acquire some ex-army radar equipment, and he took it out to the university's site in Oxford Road in Manchester. And it was totally useless there because of the interference from trams, which in those days went up and down Oxford Road. He found out that about 20 miles south of Manchester, the botany department had a couple of fields where they did crop trials, I suppose. And they had these two wooden huts in which they sort of had their coffee and did all the things that you have to do. And just note that little sapling on the lower left. I'll come back to that later on. Anyway, they got the equipment out there, I think actually on the 13th of December, 45. It was very cold, and it took about a day before they managed to defreeze all the fuel in the generators to get the system going. But then on the 14th of December, they got the first echoes. And here was a wonderful piece of serendipity. It's a wonderful word. I think they said it was the nicest word in the English language a couple of years ago, because that coincided with the peak, or just after, of the Geminid meteor shower. And in fact, the echoes they got were not from cosmic ray air showers, but from meteor trails. As a little dust particle comes in the atmosphere, it leaves a trail of ionized gas. So the free electrons, in fact, reflect radio waves. So anyway, that wasn't what he was aiming to do, but it was interesting, and they carried on doing it. And gradually, they carried on doing some more things as well, some different things. And the university brought the next field up. If you can see my pointer, Lovell was down off the right-hand side here, and this was our Jodrell Bank experimental station. We'll come zoom in a bit in a minute or two. There it is, and you can see the powerhouse. This is where we had our diesel generators, no grid in those days, and a number of antennae. Now I'll just go back one, if I may. I may have should have done that. Let me just say where it is and why it has the name it has. If you come south from Manchester on, I think it's the A34 going south, you come along from a place called Chelford Roundabout, you go along a nice flat bit, and then you suddenly dip down. It's about here. And in fact, if you actually look at a very covered up notice board, it says Beagle Bank Quarry, because that's over here. You then come left a bit, and the main road comes down here, flat, and then drops down again to a little hamlet called Jodrell Bank. And that's why it got its name. So what does the bank mean? Well, I think it's where a stream has worn away the Cheshire Plain to give you a little bit of a sort of a dip. And that's how it appears. So there's Jodrell Bank. It's on the way between Alderley Edge in Cheshire, which is a very posh place, and Holmes Chapel, which is just by the M6. And my friends that live there call it Holmes Chapel because it sounded a bit posher. Anyway, we'll zoom in a bit, and here you see it. Now, what you're seeing here are some of the earliest antennas we had. And the one that's really important is over on the right, and you can't really see it. And that's because the 218-foot diameter parabolic dish was basically made up of a wire mesh, which is invisible. It's actually here. But perhaps you can just see the little white tip at the top here. That's the feed at the top of this mast, and the signals received by the telescope came down, amplified here, and then over to the observing room over here called Park Royal, as it happened. Now, you might well say that an antenna just looking straight up is not really much use. But of course, as the Earth rotates, a strip of sky all the way round comes over during one day. And by altering the angle of that mast a bit and tilting it sideways, you could actually look at strip upon strip upon strip and then build up a radio map. Now here's Lovell. I think it was on the day he became Professor of Radio Astronomy with his staff, some of whom were still there when I became a student there in 1965. This was my supervisor here, was here. And over here in Chinchat, Dr. Tom Kaiser. Now he was actually a communist sympathizer, and some of the staff were having Russian lessons in the room above the Red Lion pub at Goosetree, and it was thought he might be a Russian spy. So this guy here, although he was doing a PhD, was also an MI5 agent called Ian Brown, here to keep an eye on Tom Kaiser. Anyway, there's that big dish I mentioned. Now, it made some very nice discoveries. And there you can actually see with the dish, the pole tilted, we could look at different strips around the sky. So over time, they were able to make a crude, that means low resolution radio map of an area of sky that passes overhead, quite a wide area of sky. And this actually is a much later picture, but it shows that telescope rather better. Can you actually see that curve of the dish there? It's still a wire mesh. The mast is actually tilted, and so they could actually adjust the feed here. That was the powerhouse. These were the various laboratory rooms that we had. In fact, I lived in here, the moon hut, for quite a long time because I was doing moon radar. There were the two huts I mentioned earlier. This is the botanic part. And you might just see a bit of a bush there. That's that sapling. And I'll tell you that now completely envelops that particular hut. You can barely see it anymore. And I also just want to point out this little dish here. It's a parabolic dish. It's fully steerable in that on the two towers, one on each side, it can be tilted up and down. And on a central pivot here, it can be rotated round one way and the other. So it meant it could actually point to any part of the sky, but also it's possible to track an object across the sky. And that means you can integrate the signal and detect weaker signals. So that was the site sometime earlier, but it just shows you this telescope quite well. Well, they made some very nice discoveries with that telescope. I think the two most significant, first of all, in the radio, they detected the remnant of Tycho's supernova of 1572, which is completely invisible in the visible part of the spectrum, but shows up quite nicely in the radio. This is not our map. It's a much more recent map of the.
Ian, you need, sorry, you're on mute suddenly.
Unmute.
Thank you.
Sorry, I don't know how that happened. Can
you
you hear me now?
Yeah, no problem.
What did you miss? Anything?
Just what you were saying. You just explained about the supernova of 1572.
Okay, fine. All right. And I've got to move away that window. I don't quite know how can I do that. And the second thing was please move this window away from the application. Oh dear. I don't know how to get rid of that. Hold tight. Previous. Are you seeing that window in front? No?
Yeah, we can. It's
Yes,
disappeared. It's disappeared now. I know it's kind of fading.
How can I get rid of that?
No idea. Where is that window from, Ian?
Please move this window away. Oh dear. Hasn't happened to me before. No, I'm just going back, aren't I?
It seems gone, to fade. Ian, it's gone now. Yeah.
Yes, okay.
I wonder if it's when you move your mouse
coming
over.
back.
Yeah.
I'll tell you what, I'll try and use another way of going forwards. Oh dear. I don't know what to do that.
And don't worry, we can all see the
okay, well, it may go away
yeah,
again.
Yeah.
Okay, now the most significant thing that it was able to do was to make, as I said, a crude radio map of the Andromeda Galaxy, M31. And it showed for the very first time you could detect radio waves from an object well beyond our own Milky Way galaxy. So this and other objects they observed showed that a big dish like that, 218 feet across, could be a very useful tool for radio astronomy. So Lovell got Charles Husband, a bridge designer from Sheffield, to design what became known as the Mark I radio telescope. And you can see the original design there. Again, it was going to be a wire mesh dish, so the backing structure was quite light. But for various reasons, one of which I think was military, they decided to make the dish surface of steel. That made that much heavier. The backing structure had to be a lot heavier too. I think that opened up a problem with the design that I'll come to later on. So here they're laying the railway track that the telescope rotates on. This is the central pivot about which it rotates. And there you see one of the two towers. being constructed. At the top, and it's just hidden by this blasted thing, and I can't seem to get rid of it. Previous. There. All right, it's gone for the moment. Right, now is basically the system by which the dish was rotated. There was something like a 30-foot diameter gear train, and that's just behind that little disc you can see on which the steel was attached. There was then a cone that went down to a very large bearing. Obviously, that's what made it rotate. And there were two pinions acting on that gear ring. And by applying a bit of opposite tension, you could get rid of backlash. Now, they were second-hand. They came from a battleship that was being dismantled at Rosyth Dockyard, and they were basically there for 15.5-inch gun turret mountings. And of course, rotating a big gun in azimuth is not dissimilar to having to rotate a big dish in up and down in elevation. And there you see the telescope coming towards the end of its construction, or partway through anyway. And you see the shape of the bowl, which was actually quite deep. That actually meant that the feed was within the aperture, which was very good for interference, but not particularly good for efficiency. Because if you have a feed up here, up there, it's very hard to send signals out at 90 degrees to be reflected by the outer surface, which of course has got quite a large area. So that was changed later on, as we'll see. There are the two motors that actually drive the telescope around in azimuth, the two on each side. And that's another picture towards the latter part of its construction. And here, looking down from above, you can actually see the construction of the mast that held the focus box and the feeds up at the top here. So that was it, getting towards the end, and you see the foundations, which I think are beginning to need a certain amount of reworking. And behind it, you can actually see a little bit of the control building here. Now, some of you may remember the Tacoma Narrows Bridge disaster, when in steady winds, a bridge began to oscillate and break up, as you see there. Lovell gave a talk about the Mark I radio telescope at the National Physical Laboratory at Tellington. And afterwards, someone came up to him and said, "Sir, have you actually tested a model of this in the wind tunnel?" And Lovell said, "No." He said, "Well, I think you should." And they built a 10-foot diameter model, and in the wind tunnel, it lasted about 5 minutes. And that's because they were solely trying to make it rotate with those pivots at the center. And it had a very large moment of inertia. It's like if I held a bar across with my two fingers in the middle, I'd have very little control. If I hold it at either end of the bar, I can control it very well. So they had to add what they call the wind stabilization girder, which you can actually see behind Lovell here. And that was to actually apply friction so the telescope couldn't oscillate in the wind. And there's a very nice view of the telescope here from the original telescope. This is the one, the 218-foot I mentioned here. And you can see the Mark I telescope with its wind stabilizing girder. I just would like to point out that's the telescope I mentioned, the little 30-foot. Now, I think you'll agree that the design of the Mark I is pretty much the same as the design of that, just scaled up. And in many respects, it was. But I'm going to come ahead in time for a minute because I think it's interesting. Can you see there, there's another dish. This was a 50-foot dish. And we used that at Jodrell Bank to monitor the signals from the Apollo 11 spacecraft and all of the other craft, including, of course, Apollo 13. And we actually tracked Apollo 11 down to the surface. We saw it going down under computer control, a very nice, gradually reducing speed. But then Armstrong, who was piloting it, saw they were about to land in a crater. So he took manual control, he lifted the craft up a bit and wiggled it across the surface, and they landed beyond the crater. It's, some people say, with about 15 seconds of fuel to remain. Well, we have that plot, and on one television program by Canadian television, I described what we had seen at Jodrell Bank intercut with Buzz Aldrin saying what they had actually been doing, and it matched perfectly. This, I think, was very good proof that the Americans actually went to the moon. This is the Lovell control room. Sorry, I say Lovell because that's the new telescope, the Mark 1A control room. I've got that wrong too, it's the Mark 1. Now, a problem. The engineers who were commissioning this analog, mechanical, electrical, analog computer, which drove the telescope, walked off site. They were not being paid. Husband was about to sue Lovell for non-payment of fees. And I heard quite recently that the university were about to sack Lovell because the cost of this telescope had overrun. There was no real money to pay for it. Well, happily we were saved. Excuse me. We were saved by the launch of Sputnik 1. The military were very keen to know if you could actually detect rockets by radar, to give us an early warning radar system. So phone calls must have gone out from the Ministry of Defense. The engineers came back, they commissioned a telescope in super quick time. A very powerful radar was attached to the telescope, and not long afterwards, on the 12th of October, only a couple of weeks I think after the launch, the third stage rocket that had put Sputnik into orbit, and which was itself in orbit, was conclusively detected. And here's Lovell showing the press the trace of the radar that we got. Well, that changed people's ideas about the telescope. It was thought perhaps to be a white elephant and a waste of money. It was shown, however, that here in the UK, we had something that no other country had. And for quite some time, we assisted both the Russians and the Americans in their space tracking activities before they had their own dishes that could do it. We tracked Lunar line down to the surface. We were told by the Russians exactly what was going to happen, and that was so we could prove it did happen because the Americans were a bit skeptical. And in fact, this one crash landed and the signal stopped, and some Americans said, well, they just switched off the transmitter. But we'd actually tracked it down to the surface. We knew precisely what was going on. We were also asked to help the Americans. They built quite a large enclave, if that's the word here, some of their communication antennas, because they didn't have a tracking system for their very first rockets. A lot of the equipment came in this big trailer you can see here, being towed along. But on the side, it said, Project Able, US Air Force, Jodrell Bank. And that was seen by a journalist of the Manchester Guardian. It was the Manchester Guardian in those days. And the story was out. And we got a bit besieged by the press. Well, the very first rocket they launched exploded not far from the pad. Actually, Lovell was quite pleased because that afternoon he was hoping to play cricket. He was the captain of the local cricket team. The second of the launches, however, was very successful. It didn't quite get to the moon, but it did in fact discover the Van Allen radiation belts. And we used our telescope both to command the separation of the stages and also to pick up the telemetry that was coming back from the rocket. I arrived at Jodrell Bank as a young student in 1965 in September, and I was given the horrendous PhD project, which was to map the moon by radar, which we did manage to achieve to do. We built an aperture synthesis radar. The effective diameter of our telescope was about 43 kilometers. However, while we were sort of working on that, the following spring, the Russians launched the Lunar 9 spacecraft, which soft landed on the surface. And we were picking up telemetry, and it looked as though it was beginning to send some signals. Now, prior to that, we had actually sent some signals via the Echo satellite, I think, using Muirfax machines. They were used in the days before the interweb to send pictures around the world. And it was thought that if we had a Muirfax machine, we might be able to decode the pictures. We haven't got one. The Daily Express brought one down from Manchester. We hooked it up. Now, all the posh people were up in the main control room, the one that you saw a picture of earlier, but I was actually down in the sub-basement where the Mufax machine was, and also the technician from the Daily Express who was going to process the pictures. Because what happened was, as the signal came in, a little stylus moved back and forth across the photographic plate, exposing it electrically. And this, of course, had to be processed. Now, my hobby then and now was photography. I helped him process that plate. So I was one of the first 2 people in the Western world to know what the surface of the moon looked like, which I guess when you're 21 is quite exciting. That was the picture. Now, it was quite late. I got home, went to bed. In the morning, my wife brought me some tea, and also the picture, this one, it was on the front page of the Daily Express. The Daily Express brings you the moon. And I looked at it for a while, and I realized there was something wrong. So I rushed into Jodrell Bank, and I said, "Sir Bernard, our picture isn't right. We had to stretch it sideways by about 40%. They'd actually use an anamorphic lens." Now, the way I knew that was very simple when you know how. Anyway, Lovell said to me, "Morison," because we were all called by our surnames in those days, "Morison, the Russians have just told us," which was a bit flattening. However, I was right, and maybe Lovell said, "Well, this chap can't be too thick," and maybe that's how I got my job there, and I've been there ever since. We've quite often been asked to search for missing spacecraft, usually by NASA, and in both cases we failed. The one on the left, in fact, we think blew up when they tried to fire the retro rockets to slow it down. And one on the right was meant to touch down on the surface, and it was meant to stop its descent engine as these little pads touched the surface. It looked as though that when they opened the pads out, the shock actually switched the engine off and the thing crash landed. So that was a bit sad. However, you may have heard of Beagle 2, and that was a very small spacecraft to be taken to Mars by the Mars Express spacecraft to land softly on Christmas Day 2003. A little probe went out to try and take some soil samples underneath a rock, take it back inside where they do some processing to see if there's anything interesting. And it turned out I was a very minor project scientist on the Beagle mission. These things have got very low power, so they transmit to an orbiting spacecraft above, which relays the signals back to Earth. The Mars Express spacecraft was not going to be in the right orbit for about 8 days. Now, our Mark I, now the Lovell radio telescope, is quite capable of picking up such a signal direct from Mars. It is, in fact, the best telescope in the world to observe and receive signals at a relatively low frequency. It was 408 megahertz, I think. All the latest big dishes are designed in a different way, and they're not very good at low frequencies. So I was asked to set up a receiving system to pick up those signals directly. We built a fantastic receiver with great help from Birmingham University. It included some high temperature superconducting filters to try and get rid of all the UK interference. And so it really was the best receiver ever built in the world at that frequency. And we went out there at about 5 o'clock on Christmas morning, and over a whole month, we observed whenever Mars was above the horizon. And there were times when they tried to get the little Beagle 2 to transmit. Sadly, we never picked anything up. We had a very nice computer display produced by one of my colleagues. If you look at this, it's called a waterfall display. This is frequency, like going across the FM band, perhaps. And this is time. You probably, actually, there are waterfall displays in radio receivers, aren't there? Can you see a vertical line there? That is a signal which is staying at the same frequency. It's something on the ground nearby. And there's another one there. But I think you might just see that little arc there. That's changing its frequency quite quickly. The Doppler effect, that's from a satellite orbiting the Earth. And also, there's a very faint line up here you might see. That's changing frequency quite slowly. That's actually a satellite orbiting the Sun. And Beagle should have been marching right up the center here, way above the noise. And sadly, nothing was seen. And we didn't know what had happened to it until only a few years ago, when an orbiting telescope was able to show the rear cover, the parachute, and Beagle itself. And sort of homing in on Beagle, it was found that two of the solar panels that should have opened, the one up here and the one down here, had failed to open. So it actually soft landed, but it didn't quite work. Isn't that sad? The saddest thing of all was that Professor Colin Pillinger, whose sort of baby this was, died just a month or two before it was found. I do hope someday someone will go and retrieve it from the surface and bring it back to Earth. Although we failed, in fact, my team were given some quite plaudits by the commission, I wouldn't say of inquiry, the thing that looked into the whole thing for our efforts to try and actually detect it. Now, some astronomy. The first and the best things that the Mark I telescope did in its early days were when the signals from a 30-foot portable telescope, you can see it's portable, were sent back to Jodrell Bank by radio link. And there you can see the radio link. It started off not that far from Jodrell Bank, up on the Cat and Fiddle on the edge of the edge of the hills in Derbyshire, and then in fact up on the Welsh borders, and then we went across the Pennines, and in fact to the interesting stage when we had a link system at the Holme Moss transmitter site, and one day the signals failed. They went up there and found the Pantechnicon had parked itself, blocking the signals. So these signals from this small telescope were combined together with those from the Mark I radio telescope. Now, that enables you, over a period of time, as you take the two telescopes, or one of them much further away, gradually from the first, to measure the angular sizes of radio sources. The first time that had been done. Many of them have got quite large angular sizes. But out of about 290 odd that were observed, 7 of them were found to have very, very small angular sizes, less than or equal to 1 arc second. And you do have one amateur astronomer with you, optical astronomer. He might know that the atmosphere basically limits the image size of a star on a photographic plate to about 1 to 2 arc seconds because of the atmospheric turbulence. You can get over that now by techniques, but not in those days. So these would look like stars. And they were actually given the name quasar, quasi-stellar object, looking like a star. You must have heard of that term. And it was first thought they might actually be some rather special stars in our own Milky Way galaxy. And there's a picture, though. When we finally got the precise location of it, we could see that it wasn't actually a star. That's a star, that's a star. This looks like a star, except there's a jet. And also at about the same time, we were able to make a crude radio map showing there was a core, which would be right in the center there, and a jet. And the two agreed perfectly. So it was, in fact, coming from a very distant galaxy. And Martin Schmidt in America was able to get its spectrum and showed that the spectral lines of hydrogen were shifted by about 17% to the red. No redshift had ever been found that great before. And you could work out the distance, about 2,500 million light years, 1,000 times further than the Andromeda galaxy we first observed at Jodrell Bank in the radio. So these were very distant. This must have been a very, very powerful radio source. And in fact, I'm an amateur optical astronomer too. In fact, some people now say I'm a professional amateur as I write books about it. I have a 12-inch telescope and I can actually observe that particular object from my back garden. Now, the energy from the sun comes from nuclear fusion, but that wouldn't be enough. And it was surmised then that the energy must come from the inflow of material towards a central supermassive black hole. And that way you can extract not just under 1% of the mass of an object into energy, but up to 30%. So I think from that, we got the idea that at the heart of these objects called quasars, we have these supermassive black holes. And of course, they've now been discovered in detail and even imaged, as some of you will know. So that was actually quite interesting. By 1972, I'm just going to try and move. It just does not want to move. It's frustrating. I do apologize. It's never happened to me before. By 1972, the steelwork, particularly at the top of the two towers, here and here, was showing signs of metal fatigue. So the telescope was very extensively rebuilt. Two big semicircular girders were added here to take much of the weight of the bowl, but to balance it about the center of gravity, about the axis of rotation, they had to build a new surface here, which was above the old, which is there, about 40-foot gap in the middle there. And this was more efficient because you could illuminate the edges a bit better, but also much smoother. So it became a much better telescope. It's a horrible name, and on its 30th birthday, we renamed it the Lovell telescope, which is the name I'll use from now on. The radio waves are brought to a focus, as I'm sure you know, by the parabolic dish. That focus is just under the focus box, a little black thing there, that's the feed. It goes into the focus box where we have our receivers. They're very small now, for a few centimeters in size, using some quite clever transistors, but not vastly better than the little receivers you have on a satellite dish, to be frank, and some of you may use them as well. However, we do make them a lot better, and instead of costing 20, 30 quid, ours cost about 20,000, because we actually put them inside a cryostat, that means cold, and we cool them to about 12 Celsius, 12 Kelvin, I should say, using compressed helium, which we evaporate. So they're very cold, and that means that the radio noise is very low. The only sad thing is that those receivers are now about as good as the laws of physics enable us to make. So whereas in the past we've been able to improve the performance of our telescope by improving the receivers, that's no longer possible. So when that new surface was built, Lovell asked his staff, what could we do with it? And Martin Walsh said, let us try and make a survey. And they surveyed a region around basically the Great Bear in Ursa Major. And in that survey, they discovered what looked like a peanut, slightly blue, which implies they're quasars, but two things very close together. And when photographs were made using the Hale telescope, the world's largest at the time, and others, it was seen there are actually three objects there. The top one and the bottom one show spikes, and that actually tells us they're diffraction spikes. These are quasars, they're very distant, and point-like. This object, the one here, does not show them. It's actually a more diffuse object. It's a galaxy about halfway between the quasars. But it was found that the quasars had identical spectra, their signatures. They looked virtually one and the same. So what was going on? It's all down to Albert Einstein. He says that if you put a mass into space, it distorts the space-time around it, and that can act as a gravitational lens. And what that galaxy is doing, it is actually deflecting the light that would have gone below it towards us. So this is a second image of that. But there's a difference in travel time, about 423 days. We get this signal later because it's had to come a longer distance. It's gone down and up as opposed to straight to us. That actually enabled us to make a measurement of the expansion rate of the universe. It's called Hubble's constant. We got a value of 68, about plus or minus 12, not very accurate, but it was actually right. In those days, the optical astronomers had values, one group had values around 50, one around 100. And now the best values are somewhere between about 68 and 72. So I'm quite proud of that. We had a bit of a close call on the 2nd of Jan 76 when we had our bit of a gale in the northwest of England. The telescope nearly blew down. The following summer, we added these cross struts here to help give it a bit more strength. We always align the towers to the wind direction when we have high winds. Okay, some more astronomy. If you look down on our telescope from above, on our galaxy from above, it would look a bit like this. There's a bar in here, a spiral, arms around it, a central bar. We're somewhere about here. Now, if you look at it sideways, there's a central bulge, about 3,000 light years in size. The whole galaxy is 100,000 light years across, pretty flat. And we're well out to one side. We can make visual and also radio maps of the whole sky, a projection of the whole sky. And there you see the Milky Way. This is called the Cygnus Rift, a nice dark region in the constellation around Cygnus and Vega. And down here in the southern sky, you don't see from here, are the large and small magellanic clouds. Now in the radio, we get a map, which I'm afraid is a rather funny color, but you can see it shows the Milky Way quite well. It also shows the large and small magnetic clouds. Keep your eye on that. And if I can go back one, can you see, just look at that. That's a large magnetic cloud, it's a large Magellanic cloud. So some things we both see. There are some things they see visually, we can't see, and vice versa. Over here is a little blue blob. That means it's a fairly strong radio source. This is, by the way, Orion. The Orion Nebula is down here. This is Taurus, and that is in fact the Crab Nebula. It's a supernova remnant dating from 1265, I think it is. What's going on? Well, stars like our own sun end up as rather small objects about the size of the Earth. But if you have a massive object that gives rise to a supernova, what's left behind is called a neutron star. It's about the size of Manchester, 20 kilometers across, and it's spinning very quickly. It has a very powerful magnetic field, which has been squashed as the whole core collapsed. And this gives rise to beams of usually radio, but sometimes light, that sweep around the sky like an interstellar lighthouse. And hopefully this will work. If I click on this, yes. And there you see the beam sweeping around. And if by chance, not always, the beam at one point crosses where the Earth is, we get a pulse of radio emission, as you see. These are very regular because these are massive objects. They change their rotation rate very slowly because they're losing energy, but essentially they're very good timekeepers. And because these pulses are very regular, we call these pulsars, as I expect you know. Sorry, I have to move on. There we go. Now, the first of these was detected by a friend of mine called Jocelyn Bell, now Dame Jocelyn Bell at Cambridge. She and I started out as students at the same time, she at Cambridge, me at Jodrell Bank. And they were actually looking at quasars, looking for scintillations, which means they were looking for very rapid changes in signal strength, which was perfect for, in fact, discovering the first few pulsars. The signal trace had little blips on it as the pen recorder went blip, up, 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 up. Now, I haven't got a recorder with me, but what we can do is to convert the radio signal into sound waves, because each time that little chart recorder pen would have blipped upwards, our loudspeaker cone would blip forwards and back, and that gives rise to sound. And this, I hope, if it works, is the sound of that first pulse. 1.6. But I made a receiver for this pulsar for a student radio telescope quite recently. There's a lovely one in the southern hemisphere called the Vela pulsar. It's about 11 times a second. Oh, I have to go on. Sorry. And the Crab pulsar, that's the one I mentioned in the Crab, it's this lower one here, that's it, is 30 times a second. Now, if I actually show you these pictures, can you see this is the central bit? There's only one star visible here. But up the top, you can just see something there. It gets brighter and brighter. It becomes slightly brighter than the other star and then fades. And that's the beam of the pulsar pointing towards us. So that's a nice, I think, visual way of explaining what's going on. Okay, now pulsars come from stars and they lie along the Milky Way. We don't see the heart of the Milky Way at all well from the UK, as your amateur astronomer will know. So we built a 13-beam receiver system, you can see it on the right there, to go down to the Parkes telescope in New South Wales, Australia. And together we surveyed of the Milky Way that was visible from there. And this discovered many, many more pulsars. In fact, the black ones had all been discovered in the northern hemisphere, and all these blue ones, sorry, all the red ones from the southern hemisphere, the new ones. And using a supercomputer at Jodrell Bank, one of our students discovered that one of these was not one, but actually a pair of co-rotating neutron stars. You can see them going round. Now, Einstein also says that if you have two co-rotating massive objects, they will emit gravitational waves, as has been proven more recently. And so gradually, the orbital diameter of these two objects should reduce. Theoretically, about 7 centimeters per day. And we can measure that at Jodrell Bank. I'm sorry, I want to move on again. And there's Einstein, one of the better pictures of him, I think. So we were able to prove that here we had at least an indirect evidence of gravitational waves. And we got the Descartes Prize, which is a European prize for that, which actually is worth more than the Nobel Prize. Now look, if these things are gradually getting closer together, eventually they will coalesce into one. This is a simulation, won't happen for a long time. The green grid is space-time. You can see there's a little ripple there. That's the gravitational waves going out. As they get closer together, the ripples speed up. And eventually, as they coalesce, you get what I can only call a gravitational wave tsunami. And that is something that has been actually observed in another neutron star collision just a few years ago. So there's that gravitational wave going out. Now, theoretically, about 2 seconds after the gravitational wave, you would actually get a gamma ray pulse. And that's later because the gravitational wave comes directly from the collapsing core, and this comes when the energy is worked out into the star somewhat. Okay. You've heard of LIGO, I hope, the Laser Interferometer Gravitational Wave Observatory. And there are 2 telescopes then, Livingston and Hanford, and there's now also one in Italy, the Virgo Gravitational Wave Observatory. That's LIGO in Louisiana, and that's Hanford in Oregon. It may just be on the border of the next state, but it's very close to the edge anyway. And this is the new one, Virgo, near Pisa in Italy. The Italians are very good astronomers, both radio and optical, particularly radio. And I'm impressed with what they do, even though their finances are a bit chaotic. Now, on the 14th of August, 2017, there was a direct detection of the gravitational waves as 2 neutron stars merge. And there are the signals. The Virgo one is much weaker because it's a smaller system, but you can see they're all there. Because there were 3 observing sites, they could triangulate and find out whereabout roughly the pulse, the gravitational wave had come from. That's the chirp, by the way. As they get closer together, the oscillations get faster and faster and faster, and finally they coalesce. And as predicted, there was a gamma ray burst 2 seconds later, which was detected by the Fermi Observatory. I know there's the gravitational wave pulse, and here, in fact, is the gamma ray pulse, which was 2 seconds later, just as theory predicted. So that was wonderful. Because there were 3 detections, they showed it had to be somewhere around here in the sky. Every telescope in the world scanned that region, and they found, in fact, where it had come from oh, someone wants to be admitted. I can probably do that. They found where it had come from. It was from a galaxy 130 million light years distant. So there's a whole new field of astronomy, gravitational wave astronomy, that's coming into action. And also, they reckon now that many of the heavy elements were actually produced by merging neutron stars, not what we used to think. We thought they were all produced in supernovae, but now they think that really many of them, in fact, come from these events. So if you've got any gold or silver around you, think of a pair of neutron stars merging. Black holes, a little bit about them. It's very hard to actually see a black hole, although there is now, as you probably know, at least a picture of the shadow of a black hole. But if you have a black hole in a binary system, that's where you've got two objects co-rotating, matter can be pulled off from the companion star and you get X-ray flares. And that's the idea. Here's the black hole. Matter comes off here, it accretes as an accretion disk, it spins up and up and up and up and up, and you get friction. The temperature close to the black hole reaches a couple of million degrees, and that gives off a lot of X-rays. And in Ariel 5, in 1975, Ariel 5 discovered the largest X-ray flare that's ever been observed. It came from a point within the constellation Morison, but they didn't really know where it was. I'll tell you when it was from here. It went up rapidly on the 8th of August 1975. That was the previous largest flare. Look at what this one did. Now, what do university staff do in August? Someone might say go on holiday. And everyone at Jodrell Bank on the staff was on holiday except for me. And that's not because I'm a goody-goody. It's because in those days, we had the Barnaby holidays at Macclesfield. We were a silk town, and we had a 2-week holiday in June. And I had my holiday then. So I was the only member of staff who was academic staff who was at Jodrell. And I got this phone call saying, can you have a look at this region of Monoceros to see if you can find any evidence of a radio signal and discover where it is. I immediately went over to our Mark II telescope, you see it there on the left, and I did a survey of that region of the sky and saw nothing. And that's not too surprising. It appears the radio energy didn't come until a bit later. But about a week later, we had access, we'd lent it to one of our other dishes about 13 kilometers away, and the two can be used, and we had developed a very sensitive interferometer which could measure positions very precisely. And I've been using that with my student to study these quasars I mentioned earlier. We had a chart recording in those days. We set up a system. We had a chart that had these little wiggle lines all the way across it. The center of that chart was in the middle of our lab. It was probably 30 feet long. We actually discovered it 2 inches from one end. We were very lucky. So we'd actually found the precise location of this object, which was assumed to be a black hole. And in fact, we got its precise position. There it is down the bottom. Don't worry about it. That means you can look there with an optical telescope. You can't see the black hole, but you could see the star about which it was co-rotating. And we know that star was a type K7, a bit smaller than our own sun. You can calculate quite easily from observing the star what the combined mass is, and from that you can actually get the mass of the unseen companion, 9.7 solar masses, and that's got to be a black hole. So this was, in fact, it still is the nearest black hole that we actually have to our own Earth. It's about 3,500 light years away. So that was quite fun. For a few years, I was a project scientist here at Jodrell for Project Phoenix, which was a NASA project initially taken over with private funding by the SETI Institute to search for ET using 2 of the world's largest radio telescopes. Over about 5 years, on and off, we observed 220, I think it was, sun-like star systems, some which we now know have got planets, to see if ET was phoning home. Sadly, he didn't. The equipment came to Jodrell in 1998. We observed 820 star systems out to 200 light years. But that's important. Our Milky Way galaxy is 100,000 light years across. 200 is nothing. It's our backyard. Unless intelligent life is very, very common, we could not expect to observe it. So did our system work? Well, you might say we didn't detect anything. How on earth did we know it worked? Well, every day before we actually began our observations, we observed Pioneer 10, then 10 billion kilometers away from the Earth, had a 3-watt antenna gain of 10, and we could both pick it up. So we knew that we could pick up signals from beyond our solar system. It was about 10 times our detection limit. And actually it died pretty much the same time as we ended the Project Phoenix. Should we be surprised? Well, I've already said no. To be honest, I do give a talk about the search for life in the universe. There are 2 major problems. One, you've got to get from single cell life, which I think might be very common in our galaxy on other planets, to multicellular life. And that's actually a very difficult transition. It may only have happened here on Earth once, about 2 billion years after the first single cell life was formed. And then the planet's got to keep a very stable temperature for a very long time. Our big moon has helped that. I don't think it will happen very often. I honestly believe that we are, at the moment, the only intelligent life in our Milky Way galaxy. But that's another story. This is a fun thing, another little aspect of astronomy. Evidence of dark matter. We observed a galaxy called M33. I've taken a photograph of that with a rather lovely telescope in Spain, using it remotely. It looks like this. And from the images and knowing the distance, we can work out its size. And we can also get measurements of the mass that we observe. It's called the mass to light ratio. If we think that stars and things there are the same as in our own Milky Way, we can estimate the mass. Okay. Well, we have a 7-meter telescope we set up for use for our students at Manchester University. It's still being used, and I helped develop and set this up with a receiver. And it's a spectral line receiver. That it's measuring the amount of, in this case, the hydrogen line over a range of frequency. Now, these big spikes here are due to the fact that we've tried to get rid of the effects of our own Milky Way galaxy. So ignore that. But over here, when we're looking at M33, we get this rather broad band. And you can perhaps see the width of that band is about 200 kilometers. All right, plus or minus 100 kilometers, about the center. Now that actually is the speed measured, but the thing's at an angle, and from the angle it is to the Earth, we can get an estimate of the actual rotation rate of the outer parts of the galaxy. It's about 160 kilometers per second. And from that, you can actually measure the mass. And what you get is 45,000 million solar masses. But the mass determined by the light to mass ratio is only 8,000. So that tells us there's about 5 times more matter we can't see. We call that dark matter than normal matter. So that's, with a very small, simple system, you can actually detect the presence of dark matter. The Lovell telescope was getting a bit wear-worn by the end of the last millennium, particularly its surface, and we were given the grant to take away the surface, to clean the backing structure of rust, and replace it with now galvanized panels. There you can see them putting them in. So they shouldn't rust. And it has a wonderful new 2-pot epoxy surface, which shouldn't need replacing for about 15 years from when it was actually put in around 2002. And there you see the work going on. Part of it's been done, and part was still ready to be done. It looked rather fine one Christmas, actually, it's January the 2nd, because we'd done this part. They put some trial paint on this bit, and here every alternate one had been done. It looks incredibly rusty, partly because that was taken at dawn on January 2nd by me, and it does rather highlight the rust. That was, of course, being released as you actually stripped off the panels. Anyway, now we have a wonderful new surface, better than it ever has been. And that's a rather nice picture showing the moon as well. And for a reason I'm going to come to, I promise you, hand on heart, that telescope is now better than any time in the whole of its history. In fact, we've just finished a third upgrade where the old surface, which was underneath here, has been completely replaced. We had some celebrations for its 50th anniversary. And because I was a radio amateur, as some of you may have noticed, I was asked if we could reproduce the moon bounce that they did using the Lovell telescope when it was first built. Now, of course, there were signals being sent from the Lovell telescope and received by it, and that's pretty easy. However, our Lovell telescope could only receive. So I had to try and set up some systems or get people to help us do some moon bounce where the Lovell telescope received only. In fact, I was able to use a 21 element Tommer, and as I'm an amateur optical astronomer, I actually had a mount that was tracking the moon through the clouds. So all day and the day before, I was actually tracking the moon with that antenna. I was loaned a fairly powerful 70 centimeter amplifier. We actually changed the receiver system on the Lovell telescope to pick up 70 centimeters. And in fact, on the day, I was able to actually send CW from my home in Macclesfield to Lovell, to the Lovell telescope. But we'd actually got people coming in from Australia, America, and the Arctic Circle using much bigger antenna. It was interesting that the guy in America had stacked Yargin on top of his Land Rover, but he couldn't get the elevation right as it would be. So he went out and bought himself some of these things you can put your wheels up on to lift the car to get the angle right. That all worked rather well. I wrote it up for Radcom. I don't know if I can show. Can you see the picture of the Lovell telescope there? You might. And to be honest, surprisingly, at the end of that year, I was awarded the prize and a plaque for the best technical article of the year. So perhaps I am a, what's the word? An award-winning writer. I don't know. Anyway, that was quite exciting. So let's move on. The Lovell telescope had a new drive and control system, so it can track more accurately. There were actually 10 computers now on the telescope, all working together to actually allow the telescope to, I'm just admitting somebody, to drive around more accurately. Now, the thing that I spent, probably 10 years of my life at Jodrell Bank was in fact helping to design, build, commission and use an array of telescopes called Merlin. You may or may not have heard of. Not many people have. This is the idea. We have telescopes around the country. The home station is the Mark II telescope at Jodrell Bank, the one I'd used to try and find the black hole. We have new telescopes at Tabley, Knockin and Darnhall. They were the first three new ones. We have a telescope down at Defford that was part of TRE Defford. And we then built, a bit later, a 32-meter telescope at Cambridge. So that's the array that we currently have. We're hoping to extend it, in fact, down here to the Lizard Peninsula, down to Goonhilly Down, and use a telescope there to link in, which will double the size. That will be fantastic, hopefully in the next few years. Somebody else is coming in. This is the Knockin telescope. I had a lovely summer down there. It was the first of our new telescopes, helping to commission it. Every day we'd call in at the shop, the little village, just a pub, a church, and one shop. And we got our sandwiches, etc., to have for lunch. Anyway, there's a new owner of that shop, and this is a sign he put up outside some years ago. So that was a very happy summer in my life. We use a double telescope in Merlin. It doubles the collecting area, and that makes it one of the most sensitive systems in the world. We have exactly the same resolution in the radio as the Hubble Space Telescope has in the visible. So we can do a lot of matched observations. For example, you may remember the Hubble did this fantastic observation of the deep field. We've observed it too. One thing we can do, we can't see nearly as many galaxies, but we can measure their positions very accurately, and that enabled a lot of work to be done by other astronomers working on the Hubble Deep Field. Now, since the millennium, we've upgraded Merlin. It's now called eMerlin. We've actually got fiber optics linking up every telescope to Jodrell. They have a capacity of 30 gigabits per second, which is pretty good. And that's made it very, very sensitive. And also, of course, we have very high resolution as well. So it's one of the world's top arrays of radio telescopes. We're now actually observing the Hubble Deep Field again, but looking at individual galaxies and trying to see how they evolved in the earliest days of our universe. Some of you may know that Betelgeuse dimmed around Christmas time, not this last Christmas, the one before, and we'd actually shown that in fact it was becoming asymmetric, and we think it had outflowed a great bubble of gas and material, and as I see on the picture on the left there, that dust had actually obscured some of the light from Betelgeuse and made it appear less bright. That was really rather nice, linking radio and optical astronomy. We also have a role of the Lovell telescope and the Cambridge one in particular in what's called European VLBI. This is linking up telescopes all over the world. So this is almost the last example I'm going to show you. There are two very nice galaxies, M81 and M82. They're actually in Ursa Major. And this top one, if we look at it in detail, this is a picture from the Subaru telescope, has a load of rubbish coming outside. This is H-alpha emission. In the heart of that, there are supernovas going off around every 32 years or so. It's what we call a starburst galaxy. But you can't see what's going on because of all the dust. But in the radio, we can. And with Merlin, and also using a telescope in America called the VLA, all these little white spots are supernovae. And we can observe over time these white spots getting bigger. And we can measure the speed at which they're expanding. But we'd like to do better. You'd need to have a telescope that was at least 10 times bigger than Merlin. And we get that by linking telescopes all over Europe, as you see there. I suspect the one in the Crimea is no longer used. And that gives us a much bigger resolution. This is the largest telescope in Europe. It's a 100-meter one in Germany. There's an array in Holland, which is equivalent to about the Lovell telescope. At each observatory, we actually use to digitize the data and store it on big tape decks you see here, and they were transported to a place called Dwingelo in Holland, where they were processed. Now things are quite different. That's our new observing room, and everything is now done. For some time, we stored the data on rays of hard disks. Now, in fact, we send it directly by fiber optic cable to Holland, and there they combine the signals. So what was basically just a little expanding blob, as seen with Merlin, you can actually see here one of these expanding, and we can actually measure detail and structure of an object in a galaxy 12.5 million light years away. And in fact, here, another example, sometime back, can you see, on the 25th of April that year, nothing. On May the 3rd, a new supernova. So that's really rather lovely. And we're a major part of the EVLA, the European Network of Radio Telescopes. This is a chart I made some years ago, and it showed the relative sensitivity of some of the radio telescopes around the world. Here was the Lovell telescope, well, Mark I actually, when it was new, at 1. The Effelsberg dish came up at about 8. We're better, we're up here, and that's up here. The VLA in America was up here, and Merlin was about the same, just a bit less. But here you can see the Arecibo dish, which is this giant hole in the ground. Sadly, it was destroyed. It collapsed, or the feed system that's hanging above it, which you might just see now there, the cables broke and it collapsed. So that's probably out of action. But the Chinese have built fast and even bigger similar telescope in China. Now we've upgraded Merlin to E Merlin, and that's now up here, which is probably still more sensitive and fast. The EVLA has more telescopes, is a little bit more sensitive than us. But we want to do better, and there's no way any single country can actually do better now by itself. So we've worked together as a consortium across the world, and we're hoping to build, and are going to build, what's called a square kilometer array. That's going to be in the northern Cape of South Africa, the Karoo, and also part of it in Australia. That's the site of it here. Almost nobody lives there, so the radio interference is very, very low. And that's a sort of idea of how it will look. These are 16-meter dishes, and that's the central hub you can see there. There are probably about around 1,000 dishes there eventually. It's going to take some time to build them all. Probably start operating in about 2025, 26, something like that. And just a point here, I used to take lots of pictures of the Lovell telescope, many of which were from the spot where I'm standing in this picture, where I took the picture from. And it's called Morison's Gap, or it was called that. It was on the plans of a new building. Because can you see how these trees nicely frame the telescope and have the same sort of shape? Well, it was decided that the world headquarters of the square kilometer array would be built at Jodrell Bank. And here it is. Those are two of those trees I mentioned, and Morison's Gap really is no more. And that's it. It is now fully complete and open. it really dwarfs our little observatory. There's our observatory. Now it's a 13-meter dish, and that's used for observing the crab pulsar, in fact, all the time pretty well. And so that's the future. It means that the site at Jodrell Bank is really safeguarded for at least 50 years, one hopes. We also hope that the Lovell telescope and hopefully Merlin can keep in operation now for many, many more years. They're both in top notch. As I said, the Lovell telescope is better than any time in its life. It's a major player in the European network, which is still one of the world's greatest radio imaging instruments. So we hope there's a good future. And really, I just want to say that it's not me you should thank for this talk, but Bernard Lovell, without whose vision, none of this would have been possible, and I wouldn't have had a job for over now 50 years. Thank you very much for listening.
Brilliant. Thank you very much indeed, Ian. That was a fascinating talk, and I know there was a slightly aggravating glitch on your presentation there, but the content was so engaging. For me anyway, it didn't detract from it. So
yes. Sorry about that. It's never happened before, so I don't quite know.
Hasn't happened to us. It hasn't happened here either, Ian. But never mind. Oh, there's always a first. ET got in there. So
yes.
Shall we open it up? Who would like to make a question, comment to Ian? Who wants to go first? Yes, Bob, GM4DLG.
Well, I did have loads of questions, Ian, but you've answered all of them as you've gone through that. What I'd like to say is, as an amateur astronomer, I've listened to many, many talks on astronomy at venues all over the place, star parties in the States and other parts of the world as well. And can I just say, that is up there with the best of them, Ian. It was a brilliant, if you don't mind the pun, synthesis, pun on interferometry, of course, of both radio and optical astronomy. And I don't think I've ever heard one that marries the two subjects together quite so well. I was absolutely, I mean, I've listened to a lot of stuff before, but I've never heard a talk that brought it together so well. So absolutely brilliant. Well done. I was really, really enthralled.
I'm sorry, I was fluffing some words. I'm still a bit tired. We spent 8 hours on the road yesterday, driving back from Penzance, having come back from the Isles of Scilly. So I'm still a bit knackered. But anyway, I hope it was okay. Anybody else?
Yes.
Hello there, Ian.
Oh, yeah, go on, Rod. Yeah, you go first and then Ray after you.
Okay, thanks. Oh, hello, Ian, and good greetings from Bradford. Hope to see you again sometime. Just wanted to know if...
Yes, hello.
Hello. Can you give us a comment on whether Jodrell Bank will be involved in the long-term study of the search for gravitational waves by the accurate timing of pulsars? That's a thing that's rather interested me in the past. So what's your comment on that?
We are part of the, I think it's called the European Timing Consortia, and I do have a talk which includes pulsars specifically, and that's mentioned in that, and I can't remember the exact name. No, we've been carrying out observations to that end for quite some time. And because we're one of the largest telescopes, and the Lovell telescope is superb for doing pulsar timing, which is what matters, we hope we'll get something. But the objects that it will detect are very dissimilar to those that have been detected by the gravitational wave detectors so far. It's a different sort of range of size. I can't remember the exact. No, we're part of it, and hopefully sometime we will detect gravitational waves. That would be great.
Okay, thank you. Thank you.
Okay, thank you, Rod. I've got Ray next, and then Alex, M0XH2.
Good evening, Ian. I'm not very far away from you. I'm just in Congleton. So I'm about 7 miles from Jodrell Bank. Down the years, we've had various news reports of, and I know if we visit the centre, we have to switch our mobile phones off. And it's always puzzled me as to whether my radio could interfere with what you're doing at Jodrell Bank.
Right. Well, look, I have to say that there's an awful lot that we could do in the past we can no longer do, largely due to mobile phones. I'll just try and explain that a bit. I mentioned the hydrogen line, didn't I? The further away a galaxy is, the more that signal is redshifted away from 1420 megahertz. And it goes down into the bands where the mobile phones are. So we can't observe distant galaxies in hydrogen line, which is why we've got to go to somewhere like South Africa to do it, which is what they're hoping to do. So that's a problem. And the other thing, of course, is just the general radio interference levels. The two things we can do at Jodrell and do well, one is pulsar timing, because we know exactly what we're looking for. Do any of you know about match filters? You probably do, some of you. If you know what you're looking for, you can make a specific filter that cuts everything else out. And so with the computer power we have now, we can actually still observe pulsars quite easily. And the other good thing is that Merlin, because we are correlating signals from telescopes widely spaced, unless you have a signal which is coherent, i.e. in phase, at 2 or more telescopes, it doesn't affect us, providing it doesn't overwhelm the headroom of our amplifiers. Does that make sense?
Yeah.
So we're basically okay. Having said that, we still get to problems. I believe that some, get this right, estate agents are using drones to take pictures of the posh houses in Cheshire. And we think one of these is actually transmitting in one of our bands. And the trouble is, it's very intermittent, so it's very hard for us to actually spot it. And in the past, I've actually gone round with an antenna, a Yagi, and spectrum analyzer in the back of a Volvo estate in those days, finding the sources of radio interference. One of them was a building in South Manchester, in Withington, I think it was. And anyway, they called up the police. They saw this bloke with this aerial. Anyway, the police rang Jodrell Bank and said who I was. And they, in fact, had a defunct some transmitter which was just operating totally badly. So we do get problems, but luckily we can still work. Okay.
Okay, yeah, thanks for that, Ian.
I've got Alex next, M0XHT, and then you're next, David.
First of all, thanks very much for the talk. It was very, very interesting. I've got two questions, if that's okay. The first one is, what factors go into deciding where you put a new observatory, a new site? Is it just areas where there's no background RF, or are there other factors that are involved? And the other one was, when you have these multiple arrays and dishes separated across continents, how is that data merged to form one image, if you will? Is it they're all looking at specific sites and the data's sort of pasted together, or are they all looking at the same thing and the data's correlated and sort of compared for high spots in the readings and so on? But thanks again very much for the talk.
Okay, I'll try. First one. Well, I think you would never build the Lovell telescope where it is now because of all the interference from Manchester and the like. However, it is actually in one very good place for one good reason. What do you think is a real problem with a very large radio telescope? It's snow. If it's snowing badly, we've got the telescope at the zenith and the snow will fill it up. And that's a lot of weight. And that could be really dangerous. And the interesting thing about where Jodrell Bank is, and the guy in Congleton will probably know as well, I'm sorry, I forget what your name was, we have very, very low snowfall there. I don't think I've ever seen more than about 5 inches. And on one occasion, I left Jodrell fine and got stuck in the snowdrift on the way to Macclesfield. So that's actually quite useful. We are in the Cheshire Gap, so we do get wind sometimes. And that was a problem way back, as I mentioned. So really now radio telescopes have to be built way away from anywhere. That's the main thing. Arrays are not quite so much of a problem. Merlin can still work even with interference. Now, the other one is, how on earth do we actually make our images? Right. It's the same for Merlin as for the European network. At any moment in time, a pair of telescopes measure something about the source they're looking at. I know that you probably know you can actually dissect the sound of an instrument into its Fourier components, its harmonics. A clarinet I used to play has got only odd harmonics, the trumpet's got all of them. Anyway, basically you're measuring these harmonics, and as the Earth rotates, each pair of telescopes measures something slightly different. So gradually each pair of telescopes builds up information. And if you have, in fact, say 8 telescopes, is it 8 times 7 times? Anyway, it's factorial 8 number of combinations. And that actually gives you a lot of information, and you can actually build up an image. Now, it's a pretty poor image. Actually, with Merlin now, because we can almost fill it, because we've got such a broad bandwidth, with the VLBI, it's not quite so good. And we have to do some clever tricks to actually extract the image out of it. One of them is called, let's get this right, oh dear, get the name. What you do is you try and say, what is the simplest possible light radio distribution that is compatible with the data we've got? And it's a way, it's called maximum entropy way of trying to do it. You're looking for the simplest possible solution to all the data you have, and that's what you hope the source looks like, and usually it does. So does that help at all? It's a bit complicated, that bit, but that's the best I think I can do at the moment.
No, that's great. Thank you very much indeed.
Thank you, Alex. I've got David, G0EVA.
Yeah, I was going to ask about snow, but the real reason, so thank you very much for the very comprehensive answer. The other thing is, I'm waving my hand really, because I've got my video working instead of that blooming silly picture. So I've been having technical issues this end, and this laptop's on its last lap. It's had it. So if you see me keep looking down here, down there, it's because I'm busy setting up my noon that I got to do.
Okay,
All
fine.
right, cheers, David.
I'll go back to blank. If I can.
Okay, anyone else got a question to Ian? If I don't see you, unmute and dive in.
I'm looking for hands and things that people can put up.
Yeah, me too. Anyone else got a question to
What
Ian?
about Richard?
Yeah, Richard,
G4
GCX.
GCX.
Need to unmute, Richard.
You mentioned about the large arrays that you're making in South Africa and also in Australia. Both of them are in the southern hemisphere. So are they going to be connected to the northern hemisphere? Because you won't see anything from the north.
I get the point. Well, that's why we hope that some of our northern telescopes will still be operational for years to come. But in fact, you do see the Milky Way rather better from the southern hemisphere, and you can see a fair bit of the northern hemisphere. I mean, in the same way, although we can't see down towards the south celestial pole, we can see some way down south, not as far as we'd like from Jodrell. So you're quite right. It is limiting. Anywhere you put a big radio telescope array is going to limit you to some extent. And you might say you could put it on the equator, but there are various reasons why that's actually not very clever. So it's a good point. And yes, that's why we sincerely hope that we'll be allowed to carry on operating in the northern hemisphere. Otherwise, they'll say, no, why is the point? You know, the SKA will be able to do everything. I hope that's not going to happen.
Excellent.
Good.
Thank you.
Thank you, Richard. Right, anyone else with a question to Ian? Yes, Terry.
Terry.
Yes, hello, Ian. Amazing delivery. Well done. Does the temperature of the dish, the reflector, have an effect on sensitivity or resolution or anything? Or is all the temperature sensitive stuff up in the actual receiver?
Yes, it's a good point. Well, of course, the temperature does it will cause the surface to expand and contract, but happily, that is not sufficient it may reduce the performance very, very slightly, but nothing that worries us. And of course, all the stuff that really matters is either cryogenically cooled or whatever. And one problem, if the grid goes, we have 2 standby generators, in fact, to provide power. And the only time that I remember when it really went off for some time, one of them, the main one, was actually having its annual maintenance, or one its 6 monthly maintenance, out of action. The smaller one could not cope with everything at Jodrell. We just couldn't. So we have about everything that matters. They're on what are called uninterruptible supplies with about half an hour's worth of power. We spent that hour frantically going around Jodrell, turning everything off that wasn't absolutely necessary. And finally, at about the 7th attempt, the little generator was able to start up, because normally it started up, found it was overloaded and switched off again. So yes, that was a bit fraught, that was, I remember. But no, the temperature basically is okay.
Okay. In which case, I just wonder if you couldn't heat the reflector to melt the snow and let it drain out at the bottom.
Well, we do actually, if the sun comes out afterwards, we'll try and tilt the dish to face the sun to melt it. But we've never thought about it. I don't think we could do that, probably. It's a nice thought, though. I'll put it to them. I'll tell the chief engineer when I next see him. When I'm next allowed into Jodrell, God knows when that will be. The university is being very, very careful about everything. We're doing all our meetings on Zoom at the moment, as you perhaps can imagine.
Yes. Okay, thanks.
Thank you, Terry. Anyone else with a question to Ian? Yes, Bob again.
Yeah, one question, Ian, if I may. It's a speculative one. You showed an image of M33 and how you'd use the telescope to discover, you know, the dark matter complement of.
I won't say discover, just to confirm.
Well, yeah, okay, sorry, yeah, confirm. Yeah. You know, despite all of the amazing astronomical advances that we've had in the last 50 or so years or whatever, I'm always sort of humbled when we consider that at the moment, of all the mass of matter in the universe, only 5% of it is stuff you can actually see. 95% of it is dark. And of that, 70% of the universe is something we've given a name to. We've called it dark energy, but we haven't a lickety split what it actually is. It reminds me of the old maps that used to be made, you know, before, you know, back in the sort of 14th century, and down sort of round about South America, they'd draw an imaginary continent, and on there they'd say, here there be dragons, which made everybody feel happy because we'd given it a name. And it's the same with dark energy. We've given it a name, but we still don't know what it is. Now, that kind of, I think, you know, the whole human race should be humbled by the fact that, you know, 3/4 of the universe is made of something we don't know what it is, and we can't see it. So my question to you is there any way that radio telescopes might be able to help us eventually discover what it actually is made of?
Wow. Right. Well, look, first of all, dark matter, which is a fair bit, there are hints of it now. There are experiments way down in deep mines to try and get rid of any effects of cosmic rays, particles, and things like that. And I think just this last month or two, 1 or 2 experiments are beginning to show hints of perhaps detecting what this dark matter might be. We'll keep our fingers crossed. I've been quite worried because there's been no real, even as the experiments have got better and better and better, there's been no real sense that they've got anywhere until quite recently. So I'm hoping that will be solved sometime. As for dark energy, well, you probably know it could well be something that comes out of Einstein's general theory of relativity, the cosmological constant. He had to put something in when he thought the universe was static. And because he knew the universe, that gravity was attractive, he put in something which was anti-gravity in form, which would in fact counteract the gravitational effects of gravity, the pulling together. But he eventually realized that this was unstable, because if you had 2 objects where the balance was exactly right, if one went slightly further apart, the anti-gravity would win, and if it went slightly closer, the gravity would win. So it was an unstable equilibrium, if it existed. So in fact, we now think maybe he wasn't so wrong. He said this was the greatest mistake of his life. He perhaps wasn't so wrong, and perhaps it just comes out of his theory. It's something to do with space-time, and we really don't understand it. I'm not totally convinced we ever will. I think our human brains are probably just not good enough to be able to comprehend some of these things. And that's perhaps a good thing. Does that help? It doesn't help much. I don't think radio telescopes can really help in any way, as far as I know.
Thank you very much. Robert, will you ask after a question?
He's denied.
Am I okay now? Ian,
Yep.
Can you hear me, Ian?
Yes, I can.
Oh, thank you. We hear many times that a radio wave has come 20 million miles through space. 20 million light years through space. How
Yes.
do we know it's that distance?
Well, we don't from the, yes. I think if it's as a spectral line, like the hydrogen line, we get the redshift. And from the redshift, we can actually estimate the distance. And that basically is the way that Martin Schmidt estimated how far away the quasar 3C273 was. So basically, if we have a spectral line, we can actually measure it. If we don't have a spectral line, we cannot do that. So we need spectral lines, and hydrogen line is one, but sadly, as I said from Jodrell, we can't see it in the most distant galaxies because of poor old mobile phones. Does that help?
Well, that sounded simple enough.
It's redshift that does it.
I wouldn't have come up with that explanation. And another one, if I may,
Go ahead.
frequency of pulsars. What frequency would you listen for pulsars on?
That's also a good question. Essentially, we actually observe most of them at 600 megahertz, 600 and something, or 1420. They are, they're actually within the sort of bands that anyone can make receivers. And as I said, I actually made a receiver for that one pulsar, the slowest one, using an Arduino Due. What's the little one they have in the UK? I'm forgetting. These little baby computers.
Raspberry Pi.
Raspberry Pi. Anyway, it's the Italian version of a Raspberry Pi. And I was able actually to make a little pulsar receiver that was attached to only a 20-foot dish and worked quite well. So they are actually relatively easy things to detect. And I don't know whether any amateurs have done that, but they certainly could in principle.
Okay, I'll squeeze another one if I may. Round about 1960, 1962, inspired by Jodrell Bank and Frank W. Hyde, who you've probably heard of, I built a radio telescope on the hydrogen line. Now, I had no way of recording. I used a corner reflector for the antenna, but I did get regular pulses coming in. Any idea what the pulses could be?
Well, they might have been a pulsar. They could have been electric fences. We had a lot of trouble with electric fences around Jodrell. And so we had to go around all of the farms, within about 15, 20 miles, fitting suppressors to them. So look, I'm not saying that wasn't what you got, but it might have been. All right. But you could have detected pulsars. You never know.
I'm sure it is possible. There was no internet and even a telephone, so no one to ask. If you've just got one more time, you indicated quite strongly that you didn't believe in aliens and visitors from outer space.
Yes.
Have you ever received a signal from space that you can't explain?
We haven't at Jodrell. There's only one that I know of, which was detected by a telescope in Ohio, the Ohio State University's telescope, called the WOW signal. It was a narrow band signal, which is what we suspect would have to be from alien life forms, because they're the easiest to detect, as you probably know. That's why CW is much better than voice. It's much easier to detect. You can put these fantastic filters on it. And it had all the attributes of coming from beyond the Earth. The trouble is that no matter who's looked at that same location in space since, and I've done it as well with our system, we've never ever detected another signal. So we just do not know. It's called the WOW signal because when the guy came down in the morning and saw the output on the teleprinter or the printer, he said, wow. But that's the only one that we think we've ever had that we don't understand.
Okay, thank you ever so much for answering the questions. It's been an excellent evening.
My pleasure.
Brilliant, thank you, Robert. Okay, anyone else got a question to Ian? Roger, you have said.
Yeah, hi Ian, thanks very much, interesting. I wonder from a practical point of view, how many people are sort of based at Jodrell to actually operate the telescope, to keep it going for you, the engineering staff, support staff, how many people are actually based there?
A very good question. I don't think it's more than about 20. There's a number of controllers. They obviously look after the Lovell telescope and they work shifts. I think there are 6 of those. And then there are telescope engineers that, look after the telescope. They go around doing primary PIs, they call it, every Wednesday, checking all the greasing, whatever that has to be done. And then there's a fair number of people involved with the electronics and the computing. But it's not much more than 25. Sadly, about 6 years before I retired, all the academics, we used to have our offices out at Jodrell, and many of us were engineers as well in many respects. I mean, I designed a complete computer system of 14 computers to run Merlin. You know, we actually had them built for us, but I designed them using some very brand new chips from Advanced Micro Devices, AMD. You've heard of AMD.
Yeah.
Anyway, so a lot of us were doing an awful lot of engineering as well, but we then got divorced and sent up to Manchester, which was a pity because I didn't like having to drive up to Manchester every day. I used to go about 6:30 to avoid the traffic. So it's about 25, I think is about the right number.
Right. So some of those guys have to refill it with helium or whatever and all that kind of stuff as well.
Yes, I'm just trying to think. Yes, I mean, it's recycled, the helium, but
Right.
obviously it will leak a bit. So yes, that's the sort of thing they have to do because
Yeah.
all of our receiver systems are cooled. And on most telescopes, except the Lovell, there's probably 3 or 4 receivers on a carousel, and we can actually change frequency very quickly, you know, probably taking 5 minutes. And that involves rotation to bring the right feed into the right place, and also linear movement to get it into focus. Does that make sort of sense?
Yeah, so like changing the lens on the camera kind of thing.
Exactly. An interesting just point on that. We had this lovely new telescope at Cambridge, and they had a fantastic system for measuring all these movements, which was, I think, ultrasonic signals were sent down something and back. And the trouble is, it caused terrible interference at 1420 megahertz, which was one of our chief observing frequencies. And so Muggins actually had to build and design some simple analog systems, basically linear potentiometers to do the same thing. So you can't win sometimes.
Thank you. Very interesting. Thanks a lot.
Thank you, Roger. Right, anyone else with a question to Ian?
We've done pretty well, haven't we? Thank you.
Right, Terry, I'll give you one quick one, and then we'll give it a close. Go on, Terry.
Okay, and I also see G4 GCX. Richard has got his hand up. Yes, there's an awful lot of wow, apart from the one signal that you don't identify in this. And if I was to be talking to youngsters and explaining, you know, how wonderful our hobby is, and you know, they might like to look at getting into something as wow as what you're doing and your colleagues, how would they go about latching on to the idea that, God, that's interesting?
Right. Well, I think there are 2 routes in. I suppose there's the engineering route, someone who's got a degree in electronic engineering or computer science, or programming, because we have a lot of good programmers we have to use. So they could be what you call, you know, good support staff. As regards the academic staff that do the observing, basically organize the observing and write the papers and things, basically you've got to get a good degree, first degree, and then get a PhD. And if that's good, you might get a fellowship, and that might be renewed after 3 years. So you've done 6 years doing it as a fellow, and then you might, if you're very lucky, get a post. But there's so few of them, it ain't easy. I'm amazed I ever got one, but it was much easier perhaps in those days. And the reason I got one actually was because I'd had to do a vast amount of, I mean, look, I did physics and astronomy at university, and yet the trouble was, we had a lab. We had to do some experimental work in our first sort of 6 few months. And they presented me with a board of 100 logic gates and switches and lights and say, do something with it. And I made it multiply 2 4-bit numbers to give you an 8-bit number. And for some reason, they thought that was quite impressive. And so they gave me the most horrendous PhD project ever, which was to build a hybrid computer system that's part analog, part digital, to run our lunar radar. And they gave me the manual for the Ferranti Argus 100 computer, which we had just got at Jodrell, and told me to design something at least as good, if not better, which I had to do. So I turned into electronic engineer, and I spent a lot of my time, for example, building the systems for Merlin, you know, doing electronics and things like that. And of course, at university, they need people to teach electronics and computing. And because not many people can do that, that's all they ever allowed me to do until my last 6 years when I was able to do an astronomy course. So, you know, it's interesting. We were, all the academic staff in those early days, we built our own receiver systems. So we, you know, we knew what we had. Nowadays, you have to give the students data basically done, ready and packaged because they've just got 3 years to do their PhD. And most of us took a lot longer than that. So, okay, there are two ways, neither of which is easy. I think the fact becoming electronic engineer or computer scientist is the best way to do it, the easiest, because we're always on the lookout for good people. Okay?
Absolutely brilliant. Thanks very much.
Thank you, Terry. Quick one for you, Richard.
Yeah. Ian, in 1957, you were generating your own power in that brick building in the far corner.
We was, yes.
When the Americans came, did they bring their own generators? Because British is 50 cycles, Americans 60 cycles. And there are places in England where they've got 60 cycles equipment.
You're quite right. I think they probably must have done. I know you can convert 50 to 60. Basically, we actually had something like that, actually. You drive a motor, which then drives an alternator, which gives you the other. But I think they probably, I don't know, I wasn't there then, so I can't actually say, but I suspect they did. That was a lot of fun.
Okay, thank you, Richard.
Thank you.
Ian, can we, on behalf of Denby Dale Club, thank you very much indeed. Can we show our appreciation to Ian in the normal way, everyone? Thank you. It was a really good evening.
Ian.
My pleasure. I'm sorry I fluffed a few words as we went along, but
Ian,
Really good.
no apologies needed at all from you, particularly after your marathon drive back yesterday. So thank you very much indeed. It was a absolutely brilliant talk, and I think we all got a lot from it. So Ian, thank you for giving us the time to do it. And I think definitely as a club, when we're able to, it will be great to go and have a trip up to the Jodrell Bank Discovery Centre and you know, have a look at the presentations that you're able to put on at the centre, Ian.
next year, a brand new building will open, hopefully at the end of this year. So it would be worth coming sometime next spring, I think.
Okay, that's a good bit of knowledge. Thank you very much.
It's been my pleasure to talk to you. And it's great actually talking to amateur radio people. I do that sometimes rather than amateur astronomers because you know an awful lot more about what the hell I'm talking about. And it was nice. I like seeing Adrian, DL88DB and Mike there from Germany. And I'm sorry about yesterday.
Okay, thank you very much, Ian. I'm just
okay, guys, I'll leave you now. I've got another talk tomorrow night. God help me.
Glutton for punishment.
I know. Anyway, bye-bye, everybody.
Good night.
Thank you, Ian.
Thank you.